So we have started our chapter 3, which is equations of continuity and motion. We're doing everything right now isothermal, so there is no changes in temperature or any transport related to temperature differences. So basically we're now going through chapter 3.1, which is equation of continuity, and then we will continue to chapter 3.2, which is equation of motion. We will skip equations of energy and angular momentum and then proceed to the rest of the chapter 3. So we started equation of continuity. Essentially, we're looking at a little box or volumetric element. Right now we're in Cartesian coordinate system, but the same would actually work in any other coordinate system. It's just that the derivation is slightly more involved. And we're looking at the volumetric change of mass within that element. The moment I'm looking at mass, I'm actually integrating things over this entire element, right? Because it's something that is, mass is not necessarily a pointwise property, it's an integral property over a small volume. And pointwise property would be density. Right? So basically I'm looking at the volumetric change of mass in time within this volume element. And I know that since I don't have any reactions that would generate anything, that's not what I'm looking into right now. I'm looking at the change that it can only occur by flow through the boundaries. So my net change of, or volumetric change of mass will be net mass flow through the boundaries of this element. Okay. In order to figure out what's actually coming into the element, we actually have to know where is the normal to this and what is the inward versus outward defined normal to the surface of this element. So basically, if I'm looking at the inward pointing normal, if this is my element, it's pointing in the negative x direction on this side. It's pointing in the positive x direction on this side. Likewise, if I look at the y and z, I would have it at this bottom, it would point upwards, so in positive y direction, so that would be delta y. On this upper boundary in y direction, upper y plane, I would have, no, I'm in z direction. So delta z and minus delta z, and then in y direction, that's this front and back side, I would have positive and negative delta y respectively. Okay, so basically what's coming into the boundary, if I focus on one of these boundaries, what's coming in is essentially projection onto the inward normal, right? So when I look at this lower x side, this projection is rho v dot delta x, and that's essentially rho vx evaluated at what I'm calling x, and this upper boundary is x plus delta x, right? So I have x plus delta x, and then similarly y plus delta y, z plus delta z, okay? So on this opposite boundary, my normal is oriented in the other direction, so basically I will have minus rho vx evaluated at x plus delta x, okay? So when I pile up all of the contributions on the 6 sides of this volume, I will get that this is change in time of mass, which is density times the volume, okay, is equal to rho vx evaluated at x, that's right here, times the area of that side, which is delta y delta z, minus rho vx evaluated at x plus delta x evaluated at delta y delta z, okay? Plus the same thing I do in y direction, so this front and back, okay? Area of that side is delta x delta z, and then I proceed and do the same for the bottom z and upper z boundary. And that's, I have to evaluate, so now my projection is rho vz, because my normal is delta z, and I have to evaluate it on z here, and z plus delta z up on the upper side. So when I look at this, I can actually divide by delta x, delta y, delta z, because that remains constant. It doesn't change in time. So basically, and yes, note that this sum is essentially integrating rho v dot normal over this boundary. Okay. So I will divide by volume and sort of like send delta x, delta y, and delta z to 0. And when I do that, so for instance here, I have rho vx evaluated at x minus rho vx at x plus delta x divided by delta x. Okay? This term is divided by delta y and this one by delta z. I will actually get the d rho dt, which is what's left on my left-hand side, is equal to minus derivative with respect to x of rho vx minus derivative with respect to y of rho vy, and minus derivative of rho vz delta z. Okay? And that is actually a divergence of rho v. This is why at the very beginning of the class I said when you think about divergence, think about integrating over the surface of a volume element, in which case you actually have to project things onto the normal of that surface. Okay? So essentially, any kind of conservation law will immediately have some sort of divergence term in. So any kind of partial differential equation that is expressing conservation, it will have some form of divergence in it. And that's basically from this procedure. So this is the simplest procedure, okay? Kind of the scalar value of density or mass is the simplest thing that I could actually go and look at. I might actually have vector quantities as well, right? In which case my equations will be a little more complicated. But again, I will still get a similar procedure with divergence. Okay, so d rho dt is equal to minus divergence of rho v. Now, if I was actually in a different coordinate system, my equation, this equation that I just got here, d rho dt plus divergence of rho v is equal to 0. Okay? That equation remains the same. I just have to express it in the different coordinate system. I could have derived it in cylindrical or spherical coordinate system as well. It would look a little more complicated if I was deriving it, but the basic principle is still the same. And it would look complicated simply because my areas are not constant with location. Okay, so I would have to adjust them with the radial distance from the center of the coordinate system. So basically, that's why when you look up what is divergence of rho v or divergence of any vector quantity in cylindrical coordinate system, you will have that 1 over r ddr kind of a term sitting in there. Okay? That's because of this change in the area with the distance from the center of the coordinate system. Okay, so expect when you evaluate that, and you basically just go into the appendix and look it up. Okay, but expect a term 1 over r ddr in there, or 1 over. You will have dependence of r squared if you're a spherical coordinate system. Okay, so just don't expect it to be that as simple as it is in Cartesian coordinate system. Okay? All right. So we will have some interesting consequence that I'm actually going to write on. If I have the consequence is that if I have incompressible Newtonian fluid flowing next to the solid surface, components of viscous stress normal to the surface are 0. Let's actually, so that's basically a practice in manipulating equation of motion. So let me just open. Is this the last one? No. Oh, this is the last one? Okay. So I finished that one, then I can just open a new one. D. Okay. So basically, I will have an example. So my equation of continuity is the rho dt plus divergence of rho v is equal to 0. So first one, I guess the simplest example is, well, what happens if I have a constant density? Then essentially I will have 0 plus of rho v is equal to 0, and since rho is constant, I can divide by rho, and I will have divergence of v is equal to 0. So these are our incompressible fluids. We used this already, so it's actually a consequence of equation of continuity. So this is, we use this for incompressible fluid already. This is consequence of equation of continuity. So even though in our shell balances for incompressible fluid, we didn't explicitly say, oh, now we're going to apply equation of continuity, we actually used it simply by using divergence of v is equal to 0 in our expression for viscous stress, right? So now second example is this one that I pointed out. So if I have incompressible Newtonian fluid flowing next to a solid surface, then the normal component and by normal component we mean the component normal to that solid surface, okay? So that is implicitly said here. So normal or orthogonal to the solid surface. And that solid surface might or might not be actually parallel to my coordinate system or coordinate system planes. Component of the viscous stress exerted by the fluid onto this surface is 0. Okay, well, let's draw ourselves a surface. And I'm going to actually work on a straight surface. So I'm working on a simple straight surface that I'm going to make parallel to my coordinate system, but it does apply in general. So basically this is my x and y will be my plane, and this is going to be my z. So my surface, in the simplest case, my surface normal is delta z. Doesn't have to be, okay? So that means that if I have shear stress tau, okay, then tau zz is the normal component of viscous stress tensor on this surface, okay? So this component of stress normal to the surface. Now tau, general description of this viscous stress tensor is minus mu times what's next? Oh boy. I'm glad we didn't have a quiz today. All right. Yeah. Plus, then what? So Jacobian transposed, plus what's then missing? Times what? Divergence. And then, am I done? Is this a tensor? No, what do I have to multiply it with to get a tensor? Identity matrix, right? Because divergence is a scalar in itself. Okay? So to get a tensor, so this is a tensor version. Right? Now, luckily this part is 0 because we assumed incompressible Newtonian. So basically what's left is just this minus mu now just tau ZZ will then be what? What do I have left here? dVz, I hope that's what I hear. Okay, now I have to somehow make use of this knowledge that I have incompressible. There's something special about the incompressible fluid, okay? And I'm claiming that for incompressible Newtonian fluid, so I just applied that the fluid is Newtonian, right? This is my version of viscous stress for Newtonian fluids. Now, so what do I know? It's incompressible. That means that I already used divergence of V. So let's look at the divergence of V once again. In this Cartesian coordinate system, my divergence of V is simply dVx dx plus dVy dy plus dVz dz. And that is equal to 0. Well, I have dVz in both. So basically, I can express that my dVz dz is equal to minus dvx dx minus dvy dy, correct? And this is, I'm on the solid surface and close to it. What is true for Vx and Vy on this solid surface? They're 0. And x and y are actually parallel to the surface, right? Okay. So basically my Vx is 0 and Vy is 0. And x, y are parallel or tangential to the surface, if I had a more general case. So if I'm looking at dvx dx or dvy dy, they're not changing. There's no change in Vx and Vy along x and y. So basically these are therefore dvx dx, dvy dy are 0 on the surface as well. Again, on the surface as well. So therefore, this is 0 on the surface. Right? So then my tau ZZ is 0 on the surface. Now, if I had some general surface, so if my surface was actually doing this, okay? And there's a normal. Then this claim is not that tau ZZ is 0, but tau NN, N being this normal, right? And that N is following the surface, okay? So the claim is that tau NN, that's what I mean normal to the surface. So not necessarily, don't immediately assume that like your coordinate tau ZZ is 0. Okay. So that's it. So now I actually want you to look at the worksheet that I gave. Does everybody have a worksheet? If you don't, there's one here. And I want you essentially to go and repeat the process, but this time we will actually look at the change of combined momentum in time. Okay? Now, the main difference is that our mass was a scalar quantity, even when I integrate it. Okay. But now momentum is a vector quantity. So I will actually have to, as we always do, break things up on x, y, and z. So first we will actually look at the change of the x component of momentum, which is a scalar quantity, and basically do the same procedure as this equation of continuity. The only additional thing is that we will have is that the body force can actually change momentum, and we will add that part to the equation. Okay? And then we will simply look at, okay, so that's x momentum, my y and z momentum have to be similar. Okay? So I will basically just write down what is, or you will write down what is the case for y and z. And after that, we will actually put it together into one big, simply looking equation, but it's going to be a vector equation, for which we will have to define what is divergence of a tensor. Okay? And we will do that once we actually look at all of these components. That will basically, on the page 2, motivate what should be divergence of a tensor. Okay? So that definition was not there made out of the blue. It was made, actually, the definition of a divergence of a tensor was made to make this equation of motion simpler to write down. Okay, so that's our objective for the rest of the class. So get going. This is a little bit of an individual work, so you don't just passively write down what I do, because it's essentially the process is very similar to the equation of continuity. So you should be able to answer the questions one by one. And I will be walking around if you need help.
So on the first one, that's a comma, right? Phi xx, comma, phi y x.
Yes, comma, phi y x. So each of the individual ones. Xx, yx, z. So since movie for this will be extremely boring, I'm going to stop it. Like then 20 minutes of silence in the movie, so I'm going to